All right, a study was conducted on students from a particular high school over the last 8 years. The following information was found regarding standardized tests used for college admittance. Scores on the SAT are normally distributed with mean of 1106 and standard deviation of 204. Scores on the ACT are normally distributed with a mean of 19.1 and standard deviation of 3.8. It is assumed that the two tests measure the same aptitude but use different scales. If a student score gets an SAT that is the 32nd percentile, find the actual SAT score. So this is an inverse norm problem because they're giving us the percentile or percent of data smaller than this value. And then so they're giving us the area under the curve, and then they're asking for the value of the random variable, which is the SAT score. So here is the normal distribution of the, we'll say these are the SAT scores. And that is what is along this x-axis is this x variable, which is SAT scores. And then the mean of the SAT scores is 1106 with standard deviation of 204. Then they ask if a student gets the SAT score that is there's a 32nd percentile, find the actual score. So that means that 30% of the data, probably over here to the left, 30% of the data is smaller than that. So that means that this area under the curve to the left is going to be 0.32. So to find this unknown test score such that 32% of the data is to the left, we just have to do inverse norm. So inverse norm, this function always wants you to input the area to the left, so that's perfect for us because that's what we were given. We're gonna have to do any minus ones, and then now if we wanted to give back the actual SAT score, then we have to put the mean of the SAT scores, which is 1106, and the standard deviation of the C scores, which is 204. So we can go ahead and do that pretty quickly, and we'll use so that's the instructions to use the TI-84. You just do second bars and then inverse norm, put your 0.32 and 1106 and 204, and then you get your answer. If you use class calc, you can go stats, distance plots, normal distribution, and then you put your 1106 and 204, the mean standard deviation. Then you can go back to stats and do distance again, and then inverse, and then you just put the area in the curve to the left, which is 0.32. So I think I messed up. Sometimes it wants you to put an extra comma after the normal distribution. Now it gives me my answer. So the answer, the test score such that 32% of the values, the test scores are less than that is 1010. Actually, the 1011. Better too if you want it. Round. Oh, it says round to the whole number, which would be the round to the whole number. Okay, so let's just double check it. 11 is what we want there. Okay. Oh wait, 1011. Okay. Then they ask, well, what would be the equivalent ACT score for this student? So Z scores just tell us the number of standard deviations you are away from the mean. So that's what it's going to help us compare oranges to apples here. It is figuring out the Z score of this value that we just found, the 10, 11. One easy way to find the Z score of that is just changing the mean and standard deviation to 0 and 1 here. Then we're going to find the Z score that has 32% of the data to the left of it. And that z-score is negative 0.4677. We'll just say negative 4 point. Ideally, I would not truncate that number because I'm going to use this number to figure out my next part of this problem. So next, in other words, we just standardized that normal random variable. We found out the variable was 1110. No, 1011. Well, then we said, well, what the z-score, how many standard deviations is that away? Well, that is not quite one standard. It's like only a half a standard deviation below. It's negative 0.46. Let's get more decimal places. At least 4, 6. Let me do 5. 4, 6, 7, 6. Well, I guess I would round up to 7. Okay, so I'm just gonna do 4.677. 4.677. Okay. This is the standard normal curve with the z value. So that's the z-score of the 10, 11. That's just the number of standard deviations away from the mean. So it's a half of a standard deviation below the mean. That's it. It makes sense because it's the right of the mean there. Now, how do we figure out what ACT score that is? Well, we just have to figure out what is that that many number of standard deviations below the mean and the AACT scores distribution. So here's the ACT score distribution is 19 and 3.8. That's the mean, and standard deviation is 3.8. Okay, so if we have, if we're 0.4677 standard deviations below this mean, then where are we on this axis? Where are we on the x-axis? So one way of doing it is taking, and here's the actual formula for it. You have this new x value is going to equal the mean plus the z-score times the standard deviation, because there's this many standard deviations below the mean. So the standard deviation in this picture is 3.8. So I do 3.8 times the 0.466. So let's do that. Well, technically it's negative. Well, negative 0.46, okay. And then we add it to the mean, which is 19.1. Uh-oh, you know what? I think you have to press and get enter because it's going to follow with operations, and 3.8 times negative 0.4577. I think that was the number we got. 4677, sorry. That was the z-score we got from above. And then let me just press enter there. And then I just take the answer from above, this negative 1.77726, and then I add the mean 19.1. So that gives me 17.3322, and that is the number that we want here. Rounded to one decimal place, it's just 17.3. Just double check our answer here, 17.3. So this is the formula that we used And we just followed order of operations. We put the z-score that we found for the data value that we're trying to compare to that SAT score to this, to ACT, what ACT score would be. I plug in the z-score of the SAT score with the standard deviation of the ACT scores and the mean of the ACT scores. And I just simplify. Because we know the location of this within the SAT scores. We know it's one standard deviation below the mean. So what we do is we go one standard deviation below the mean in the distribution of the ACT scores. That's how we found this 17.3. So scoring a 17.3 on an ACT score is pretty much the same, showing the same knowledge as scoring a 1011 on an SAT score. So that's the answer to the second part. And then next it says, if a student gets an SAT score of 1473, find the equivalent ACT score. So again, they're just comparing ACT scores to SATs, and we use z-scores. We're just going to look at the z-score of this one, and then we're going to do the same thing that we did here using this formula, and we're going to go the same number of standard deviations away from the mean in the ACT score distribution. So a student has an SAT score of 1473, so we just need to find the z-score of that. So one way of finding a z-score is always doing the value minus the mean all over the standard deviation. So the value of interest that we're trying to find the z-score of is the 1473 minus the mean, which is the in this case the 11 of 06 divided by the standard deviation of 204. All of the information I input here was from the SAT data, the mean of the SATs and the standard deviation of the SATs, and a value from the SATs. So I just do that in my calculator. To find my calculator. So I do the numerator first. There's like invisible parentheses in the numerator of any fraction to do the calculation first. Be careful when you're doing your cell phone or I'm doing class calc, you have to press enter. So I do the top calculation, I press enter, then I divide, because otherwise it'll try to follow operations and it'll kind of mess you up. Okay, so 1473 minus 1106, and then press enter, because it gives us the answer already. So like that's where, okay, I definitely need to get rid of all that other stuff first. But 1473 minus 1106, and I'm going to press enter, so that, and then I'm going to take that number 367 that I got and then divide by 204. There's my z-score that I'm looking for. So I got 367 was from the numerator there, and then divide by 204, and then that gives us 1.79902. So if I just summarize this, 1.7990102. What was I? Oh dear. Was it in second 9? Yeah, second 9, and then O2. This is the number of standard deviations that z-score at 1473 is away from the mean. So what we need to do is now we need to go to this ACT distribution, which this is the ACT distribution. And we need to figure out, let's go exactly this many standard deviations, but we're going to use the ACT standard deviations, but we're below 19.1. Oh, actually, it's above. I'm sorry. This is above because it's a positive 1.79. So we're going to go 1.79 of these standard deviations above a mean of 19.131. So I'm going to follow this equation. The mean is 19.1. The z-score of this thing, that the value that we're trying to find a random normal variable for is 1.79902. And then the standard deviation in this new distribution, the ACT scores is 3.8. And then let's do this on a calculator. I need all these numbers here. So okay, I'm going to put this, I'm going to re-enter this number down below. As many decimals as I can do. I can do this. 1.799019608. You should never truncate anything if you can afford it. I'm going to do the times by the standard deviation number, which is 0.8. I believe it was 3.8 for the ACT scores. Yeah, and then 19.1. So then I get that answer, I press enter, and then now I can do 6 point, enter it again, 8, 3, 6, 2, 7, 4, 5, 1, plus then 19.1. And I get this 25.9, I think to one decimal place, 24.9. And that is our answer. So if we go that same number of standard deviations above the mean in this new distribution, ACT distribution, then we'll be at 25.9. So that is the ACT score that's equivalent to getting a 1473 on the SAT score. So let's just double check our answer. And there we go. We got it. All right, please let me know if you have any questions. Have a great day. Bye.